living in it. Now the projective plane is sort of like a real plane equipped with some extra structure, namely the points at infinity. But I'm going to start by defining it rigorously. We define an equivalence relation. X is equivalent to y if and only if x is equal to ky, where k is in R. So, and then the real projective plane is equal to the set of equivalence classes under this equivalence relation. Now, what does this equivalence relation mean? If you have a vector x, you consider all the multiples of this vector, and so the equivalence class are just lines in R3. So the real projective space, the real projective plane is the set of lines in R3 through the origin. This is how it looks. But we need a better way to represent it, because we can't just work with these lines. It's not too convenient. Now one way to represent it is to draw a plane, z is equal to 1, and mark the intersections of these lines with the plane, which will form the points, which will represent the points in the plane. But it's sort of, you can see from the picture that it misses the lines that line the plane z is equal to 0, and these we call the points at infinity. Another way to represent the projective plane is with the hemisphere. And now the advantage of this approach is that it captures the points at infinity, namely the lines that line the plane z is equal to 0. So while it captures these lines, it also captures these lines that line the plane z is equal to 0. We need to make a slight adjustment here. We need to identify the opposite points on the sphere in the plane z is equal to 1, because we only want one line to represent one point. So we identify these 2 points, the opposite points on the sphere. And with this identification, we can learn about the topology of the projective plane. The procedure is given in the picture. This is the sphere, right? You just flatten it out. Since you identify it's going to be this, you cut out a disk. You then make these cuts. You glue them along here, and so it forms a Möbius band. So the real projective plane is topologically a Möbius disk plus a Möbius band plus a disk. Lines in the projective. Sorry, where's the? Okay, yeah, I'm going to move here. Lines in the projective space. Now, by definition, the lines in the projective space are the two-dimensional subspaces of R3. But I'm just going to show why this definition makes sense. Say you have the origin, and say you have this z is equal to 1, wherein we represent the projective plane. Now, if you have a two-dimensional subset of R3, namely the plane, then it's obviously going to intersect z is equal to 1 in a line, right? Unless it is the plane z is equal to 0. So here's just the equation, right? If we have a plane x plus by plus cz is equal to 0, and we intersect it with the plane z is equal to 1, it just forms a line. So far so good. However, suppose if you have a line in the plane z is equal to 1. What we want is to find all the lines in R3 going through this line, and this is called homogenization. Consider a specific example, y is equal to 2x plus 3, which in the projective plane could roughly look like this, say. Then we want to consider all the lines going through this set. All the lines going through this set. And so here. So we started with x, y of x in 1, where y is equal to 2x plus 3. We start with this set, x, y of x, 1. We now want to, this set of points, of course, such that x is a real number. But then we want to consider all the lines going through these points. So I just scale them, right, for any a in the real numbers. I call this point big X, big Y, and big Z, and we see that little x is equal to x over a, little y is equal to big Y over a, and z is equal to a. Substituting this back into the equation, we get x over z, because z is a, 2x over z is plus 3 is equal to y over z, and we multiply both sides by z to get a homogenized equation. So, and this is what it looks like. It's a plane. So it makes sense that the lines in the projective space are the planes in R3. We have missed the line at infinity, which is the plane z is equal to 0, which doesn't intersect this plane, but we're going to return to it later. But notice also that it goes through all the points at infinity, namely through all the lines that lie in this sort of plane z is equal to 0, right, parallel to the plane z is equal to 1, and it's going to become important later. Now I'll talk about duality. In the real plane, any two points lie on a line, but any two lines do not necessarily intersect, because if they're parallel, they do not necessarily intersect. The projective plane, it solves this issue. Any two points lie on a line, and any two lines intersect at a point. Why? Because why do any two points lie on a line? Because any two distinct points lie on a line. Because a point in the projective plane is a line in R3. And so if you take two distinct points, if you take two distinct points in R3, in the projective plane, namely the two lines in R3, then you can obviously span a plane with these two lines in the directions of the two lines. And so any two points in the projective plane meet a line in a line. But also any two lines that intersect at a point, because the line is just a plane in R3 through the origin, and so any two planes in R3 are going to intersect in a line, which is a point in the projective plane. I'm just going to invoke the dimension theorem here. That the dimension of, if you V and W are your planes, then the dimension of V plus the dimension of W minus the dimension of V plus W. Right, and so since these are distinct planes, they're going to span the whole of R3. This is going to be 2, this is going to be 2, so 4 minus 3, and so the intersection is 1, obviously, so it's a line. It's a line, and it's a point in the projective plane. Now, what are the points at infinity? for each point at infinity, there is a family of parallel lines that all intersect. Sorry, that all intersect at a point at this point at infinity.